Okay, so this is the video review for rational and radical functions, the big unit test. And so we're going to start off with problem number 1, and these problems are specifically labeled at the top of each of them. I've kept the instructions that say that you should be able to complete something like this without a calculator. So put your calculator to the side. Hopefully you're able to follow along doing the computations without any kind of assistance. So the first problem here is asking you to find out what values of x will make f of x equal to g of x, and they're giving you expressions for both of them. So when we see this expression that f of x should be equal to g of x, that is telling us that we should set the square root of 4x plus 20 equal to x plus 5, and then just solve for x. So that's what we're going to do, right? The square root of 4x plus 20 should equal x plus 5, right? And the rule for solving radical expressions is if we want to get this out of the radical so we can solve, we can square as long as the radical is isolated, if we can isolate the radical, right, if that's possible, which for us it is, right? So we're going to square both sides, and in this case we can say that a squared and a square root cancel, and just to be clear on this, the 4x plus 20 is not going to be affected by the square at all, and that is because the squared actually got kind of deleted. It got canceled by the square root symbol. So we're just going to have a regular old 4x plus 20 on the left, and then we need to square x plus 5. Just be careful. You're not just squaring x and squaring 25. You are squaring an expression. So that really means, and we'll do this off to the side, we're doing x plus 5 times itself. X plus 5 times itself, this is a FOIL problem. I'll let you do that all on your own. You end up getting x squared plus 10x plus 25, right? So don't forget to get that middle extra term when you square a binomial. So this is now, instead of being a radical problem, this is just a quadratic problem. We need to solve this by setting it equal to 0, right? I'm seeing a squared show up in my problem, and so I'm going to subtract the 4x over to the right-hand side. My goal is to try to keep it as 1x squared if I can, or some positive x squared, right? So I'm not going to move right to left, right? I'm going to move left to right. So I'm going to subtract the 4x over. So it says 10x minus 4x, which is 6x. And then 25 minus 20 would give me a 5. And then the right-hand side, because I just subtracted these away, I'm sorry, the left-hand side, because I subtracted these away, would become 0. Okay, this is a factorable expression. We got lucky. We don't have to do a quadratic formula. It turns into x plus 5 and x plus 1. Right? 5 times 1 gives me 5, and 5 plus 1 gives me 6. Right? So that works. And then when I set each of these expressions equal to 0, I get two solutions. I get a negative 5, and I get a negative 1. Okay? And so these look like the answers, right? But we have to be careful. Remember, for any radical solving problem, it is entirely possible that you might get an extraneous solution. So I'm going to go back to this problem, and I'm just going to get rid of the squaring that I did. I want to look at the original problem, right, without any changes that I made to it, which was that the square root of 4x squared should be equal, I'm sorry, 4x squared, the square root of 4x plus 20 should be equal to x plus 5, right? If I plug in my values, if I plug in a negative 5 here, this says negative 20 plus 20, which is 0, the square root of 0 on the left. So this becomes, when I plug in a negative 5, a 0. And then on the left-hand side, when I plug in the negative 5, I also get 0. And so this one's good, right? I checked it. It worked out. I got 0 on the left and 0 on the right. It works out, and it is a solution. Right? And then I can do the same thing with negative 1. When I plug in a negative 1 on the right, it says negative 1 plus 5, which is 4. And when I plug in a negative 1 here, I get the square root of 16, which is also 4. And so I'd say that negative 1 is also a good solution. So just be careful. This will not always work. In this one, it did. Okay, so we're going to take a look at one where maybe it doesn't work. So our next problem, okay, is asking us to do the same thing. Essentially, the directions are just stated a little differently. They're kind of saying an if and a then instead of the other way that we saw, just saying what values. But they're essentially saying at the end here, make f of x equal to g of x. So let's do that. We're going to say the square root of 2x minus 1 minus 5 should be equal to x minus 7. And so when we look at this one, I can't square immediately, and that's because the left-hand side that contains my radical is not isolated. So before I do any squaring, I'm going to try to get the radical alone, and I can do that by adding this 5 to the right-hand side. So I'm going to turn this into the square root of 2x minus 1. When I add 5 to both sides, this becomes an x minus 2. Okay, so what I'm going to do now is I can square. I can say square the left and square the right, and same thing's going to happen. I'm going to get the 2x minus 1, again, does not get affected by the squared because the square root blocks it. Okay, and then I'm going to square x minus 2, which again, I'll let you on your paper FOIL that out. Okay, but you get this expression here. So I'm going to now subtract to the left over to the right. This is now the same thing as what we did. We get a 0 on the left, and we'll get x squared minus 6x plus 5. All right, and again, factorable expression. This factors into x minus 5 and x minus 1. And I get two solutions. I get a positive 5 and a positive 1. So again, we're going to go back up to our original problem, and we're going to see what happens. Right? Actually, you know what? I'm going to go down to the second problem. I'm going to go to this step right here. Again, just kind of ignore the squared. Let's get rid of that. Right? We use that as an operation, but our original problem after we added the 5 looked like this. Okay? So I'm going to look at this second blue step, okay, and I'm going to plug in my 5. When I plug in my 5, the left-hand side says 2 times 5, which is 10. 10 minus 1 is 9. This is the square root of 9. And then on the right-hand side, it says 5 minus 2, which is 3. The square root of 9 equals 3. That's a true statement, and so I'm going to say square root of 5. That's a good. I'm sorry, x equals 5. That's a good answer. Okay, so let's check 1. Okay, and let's just see what happens. When I plug a 1 in on the right, I'm getting a negative 1. And when I plug in on the left, I'm getting 2 times 1, which is 2. 2 minus 1, which is 1. So the left-hand side says, give me the principal square root of 1, which remember, the principal square root is the positive square root. Give me the positive square root of 1 and have it equal a negative 1. That doesn't make any sense. The left-hand side is asking for something positive. The right-hand side is asking for something negative. So I'm going to say 1 is not a solution. That is extraneous, right? So we're going to say this one was extraneous. Get rid of it. We're going to keep the 5. This is our only good, valid answer to the problem, right? So sometimes you will get extraneous. Sometimes you will not get extraneous, right? And in this case, we plugged in and we found out that 1 was a bad answer. Right, so problem number 3, again, you should be able to solve this without a calculator. Right, so these are problems where we're asking to just find a solution. It just says solve. That's our only instructions. So we said an easy way to do this type of problem is if I look at this expression and I GCF and I just kind of factor it and see what this is made of, it's made of an x and an x minus 2. And so when I look at all the parts of the denominators, all of the factors, I'm seeing that really just this has x minus 2, this just has x, this has both. So it looks like the GCF is an x and an x minus 2. So what I'm going to do is I'm going to change the second and the third fraction so that they look like the first one. I'm going to find a common denominator. So I'm going to leave the first one alone, and I'm going to put it in its factored form just so they all look the same. Okay. I'm going to look at this second fraction and say, what's missing here in the first expression, I'm sorry, in the second expression, but that's showing up elsewhere in the problem. And if you notice, the first one has an x minus 2, and the third fraction also has an x minus 2, which means that this second one is going to need an x minus 2. So the 4 and the x were already there, right? That was what my original fraction was. I'm going to bring in a brand new x minus 2. Common denominator means that every fraction should have the same denominator, and by bringing in this x minus 2, if you notice the first and the second one, they match now. That's what I'm trying to do. So I'm going to do that same thing for the third fraction, the right-hand side, right? And I'm going to say, this one has the x minus 2, but it's missing the x, right? So I'm going to say it has the x minus 2, but it looks like there's no x involved here, right? The first and the second one both have an x. The third fraction does not have an x, so I'm going to bring in an x here, and I'm going to bring in an x in the numerator as well. Right, so now the denominators all match each other. That's good. Here's why. Here's a very simple problem. If I said something like 3/7 plus 2/7 equals 5/7, everybody I think would agree that this is true. I really don't care about the denominators anymore. Because they all say 7, they're all common. The real bulk of this problem is just the fact that the numerators, the 3 plus 2, is equal to 5. That's the important part of the problem that we really care about looking at. The 7s are just kind of an extra, they are the fraction, right? But I don't necessarily care about them so much. So I can kind of get rid of these. This is the important part. So I'm going to say 10 plus, and I'm going to distribute just to save myself some work. That's 4x minus 8. Should be equal to the right-hand side, which says 5x. And if you notice, this is a very simple problem now. It went from being this big fraction problem. Once I got the denominators to be the same, I could kind of just put them off to the side and saying that's not going to affect the answer to my problem at all because they all match each other. So if I simplify this now, it looks like I need to subtract this 4x over to the right, which is nice because that just makes it x. And then the left-hand side just says 10 minus 8, which is 2. Okay, so this is my answer after I simplify and solve my numerators. But there are also extraneous solutions when I'm dealing with rational expressions. And so here's the problem here. If I go back up to, this is probably the most obvious one, the third one, okay, and I plug in a 2, the denominator of my fraction 5 over x minus 2 becomes 0. I'm not allowed to have zeros in the denominator of fraction. That is what we call an undefined expression. And so in this case, I have to take my only solution, x minus 2, and throw it away. And so I'm going to say that there is actually no solution to this problem because the one possibility turned denominators of fractions into 0 and made the expression, my original expression, not true. And that's what happened for that one. Okay, so in this case, no solution involved because our one possibility was extraneous. Okay, so let's take a look at one more example that's like this, slightly different now because my right hand side is actually not a fraction. So I'm going to go through this one. I don't need to factor anything. I have nice expressions, and I'm going to compare the denominators and say, well, the first one has an x plus 1, and it looks like the second one doesn't. And the second one has a 2x, but the first one doesn't. Right? So I'm going to kind of bring those into the problem. So here's what it's going to look like. My first fraction has the x plus 1, okay, and my numerator has a 2x. I'm going to introduce, because the second denominator has a 2x as well, I need a 2x in my first one as well. So I'm going to introduce a 2x to the numerator and the denominator. Okay, I'm going to do the same thing with the second fraction. It has a 2x already and a 5 in the numerator. I am going to introduce the x plus 1 that's showing up on the first fraction, and I'm going to say this needs an x plus 1 in the numerator and the denominator. So I made these match. Okay, and so for the third fraction, the 2, I have a choice. And here's the choice that I'm going to make. I could just make this denominator match as well and do the exact same thing that we did in the last problem, right? In the last problem, we actually made the fraction on the right-hand side, we made that one match as well, and then we just kind of tossed all of the denominators. I'm going to do something a little different here just to give you an option. So it's entirely okay. If you wanted to multiply this 2 by the 2x and the x plus 1, that's an entirely okay strategy. I'm not going to do that. Instead, what I'm going to do is I'm going to say, you know what, let me just make this a fraction, but I'm going to leave it alone. And the reason that I'm leaving this one alone is because I have this nice 1 on the bottom. Okay, so watch what happens here. I'm going to simplify the first fraction. This now says 4x squared over 2x times x plus 1. Plus, and when I distribute here, that becomes 5x plus 5 over 2x times x plus 1. And this is going to be equal to 2 over 1. All right, so I just distributed. And now I'm looking at the left-hand side and saying, hey, look, fractions with common denominators. I can add those together. I can make one big fraction. So I'm going to turn this one into 4x squared plus 5x plus 5. Like, none of these numerators actually combine. They're different terms. And the denominator is still 2x times x plus 1. And if you notice what I did, by just simplifying the left-hand side and leaving the right-hand side alone, I created a proportion. A proportion is a fraction equaling a fraction. And whenever we get this situation where a fraction equals a fraction, you can cross multiply. So I'm going to do that instead. This is just a different way of getting to the same answer, right? And it's an entirely acceptable way to do it. I chose it for this particular problem because the right-hand side was very simple. So I'm going to cross multiply, which means I'm going to take the numerator here times the denominator. That's nice. Timesing by 1 doesn't change anything. So it's going to just become 4x squared plus 5x plus 5. Okay? And when I multiply this, I'm going to say 2 times 2x, this expression right here, is going to be equal to just 2 times 2x is 4x times x plus 1. Okay, I'm going to do a quick distribute on the right-hand side here because you're going to see something nice happens. I'm going to leave the left-hand side alone just for a second, and I'm going to simplify, distribute the right-hand side. 4x squared plus 4x. Okay, so I just did a distribute from the previous step into the x plus 1. And if you notice what happens here is I get a 4x on the left and I get a 4x on the right. So when I subtract this 4x away, okay, it actually subtracts this 4x squared away as well, and they cancel. So again, I get a very simple problem. When I subtract I'm going to subtract the 4x to the left and subtract the 5 over to the right, you get that x is equal to -1. And that's my answer. So again, let's take a look. I'm going to go back and check my x equals x equals -5. Let's fix that. Okay, x equals -5, right? And if I go back and check, when I go back and check that in the original problem, -5 is fine. I can plug in a -5 here and I don't get a 0. I can plug in a -5 here and I don't get a 0. And so I'm going to say this is a good, valid answer. That is my solution. So this -5 was not extraneous because it did not make the denominators equal 0. Right? So we have our valid answer. So I use a slightly different strategy here. Right? In my first problem, I got all of the denominators to match, and then I threw them out, and I solved a simple problem. In my second problem, I just simplified the left-hand side using addition, okay, by finding common denominators. I turned my two fractions on the left into just one fraction, and then I used cross multiplying. So that's a different strategy, but it's a valid strategy. And I looked at the problem and said the reason this one's better in this case, or it's useful in this case, is because I'm just multiplying this complicated expression by something simple. If I had something complicated on the bottom and something complicated on the top, I probably wouldn't want to do that. But in this case, multiplying by 1 is very simple, so I went with that strategy. Okay. All right. So let's take a look at some rational exponents, solving with rational exponents, right? So for this problem, our goal is to try to always isolate the x. In this, we want to try to get x alone. So in this case, add 3 to the other side. So I'm going to say x to the 2/5 plus 3, right, on both sides is going to be equal to 3. Let me get rid of that little symbol there. Okay, x, when I add the 3 over to isolate, I'm going to get a 3. Okay, so now what this problem says is, okay, x to the 2/5 is equal to 3. And if I want to get rid of 2/5 as an exponent, I'm going to raise it to the reciprocal power, 5/2. Right? It's because 2/5 and 5/2, when I use my exponent rules and I multiply them together, okay, they just go away. They become 10/10, which is just x. But if I raise the left-hand side to the 5/2, I need to raise the right-hand side to the 5/2 as well. Right? So here's what I get. So now we got to figure out how do you simplify x to the or 3 to the 5/2 power without a calculator, right? So we're not going to just type it in and get an answer. So I'm going to take this and I'm going to say, well, the bottom of the fraction just means square rooting, right? Index of 2, right, as a radical. And now I have to figure out what to do with this 5. So my base of 3 goes inside of the radical. And my numerator here is just an exponent. And I can decide, I could place it out here and raise just the square root of 3 to the 5th. But if you notice, the square root of 3 is not all really that nice. So I don't really want to raise that to the 5th power. I have the option instead of putting the 5 on the inside. So that's what I'm going to do. I'm going to raise the inside to the 5th. Because maybe I can raise 3 to the 5th power. Maybe I can do something with square rooting that. So 3 to the 5th power, again, if you don't have a calculator, here's a nice way of handling this. 3 times 3 times 3 times 3 times 3. That's what 3 to the 5th power means. Simplify in groups. 3 times 3 is 9. This 3 times 3 is 9, and I have an extra one. So now it's a little bit simpler. 9 times 9 is 81. You can do that without a calculator, times 3. So really 81 times 3, which you can do just by coming off to the side. Well, 3 times 1 is 3. 3 times 8 is 24. So the 3 to the 5th power is really just 243. Okay? Again, that's not something that even I have memorized. It's just something that you sometimes have to do. So now your job is to take a look at 343 and decide if you can simplify this. And in this case, you can. 343 is 8. Remember, we just said it's 81 times 3. So I can break this up and say this is the square root of 81 times the square root of 3. Well, the square root of 81 is 9 times the square root of 3. And I would say that this is my solution. This is the simplest radical form. Right? So again, I had to use my multiplication. I had to do that manually because I'm not using a calculator. But it's something that you can do. And I had to look at factors of 243. But remember, you had a nice little hint here. You know a factor of 243. 81 times 3. And you know that 81 is a perfect square. So that's a good problem. Okay? So let's take a look at one more of these. Okay? So in this case, again, we need to isolate the x to the 2/3. So I'm going to add the 12 over. 3x to the 2/3 is equal to 12. Divide away the 3. I'm still not going to raise this to the power until the 3/2 power until x is alone. Divide both sides by 3 and I get x to the 2/3. Okay, let me move my equal sign. X to the 2/3 is equal to, when I do 12 divided by 3, I get a 4. Okay, so I'm going to raise this now to the 3 over 2 power, which means I'm going to raise 4 to the 3 over 2 power. So let's see what we get. Again, 6 over 6, when I multiply these together, is just 1, x to the 1, which is x. And then now I have to decide, how do I simplify 4 to the 3 halves power? Well, remember, the denominator is just square root, because it's 2. Okay, and again, I need to decide where I want to put the 3. But I'm going to actually put the 3 on the outside of the radical this time. And the reason I'm choosing to do this is because the square root of 4 is something nice. When we went back and look at this one, the square root of 3 wasn't something nice. I wasn't going to be able to simplify that at all. So I just put the 5 with it and decided to make it, try to simplify it on the inside. Right? With this one, because I can square root 4, I'm going to do that first, then I'll apply the exponent. So the square root of 4 is just 2 to the 3rd power, and 2 to the 3rd power is 2 times 2 times 2, which is 8. So in this case, my answer is 8. Okay, so we'll continue in the next video looking at the next page, where we're going to work with some simplifying radicals and adding and subtracting rational expressions. But this is a nice mix of problems where you're going to be asked to not